My name is Anthony Sense, and this is Physics Lab 3, Mass of a Black Hole. In this lab report, I'm going to be going over a brief introduction of the lab, the laws of motion, and the equations I used. Then I'm going to go into part 1, where I determine the mass of a black hole. I'll do some theory behind that, show you my computational model, and my results. Then I'll try not to crash into a black hole while taking a very close look, and also avoiding an orbiting planet. Again, I'll go into theory, my computational model, and my results. Then I'll wrap it all up by determining what all this stuff means, doing some analysis and some speculation in my what if section. So a brief introduction to Newton's second law of motion, or the momental principle, and its decomposition, which is very important to understanding the theory behind this lab. As we know, F net equals mass times acceleration. It also equals the change in momentum over the change in time, dp dt. Like any other vector, dp dt can be broken up. In this case, we break it up or decompose it even further into the perpendicular and parallel components. These equations correspond to the perpendicular and parallel components of net force. In this lab, I also used Newton's universal law of gravitation. We've seen this a few times before. It relates the distances and the masses of the two objects. When gravity is the only force acting on an object, in other words, F net equals F gravity, we can use F net to solve for the mass of one of the two objects using simple algebra. To start off my code, in my first computational model, I set the change in time to the time in a day represented in seconds. I also started two counters that will compile the mass of the black hole at each iteration and then find the average mass at the end. I then went into finding the initial and final momentums, finding the change in velocity and change in momentum, which, as we know, the change in momentum corresponds, used with the change in time, with F net. I then broke up that change in momentum into the parallel and perpendicular components to find the parallel and perpendicular components of net force. Then I used that algebra with the universal gravitational equation to find the mass of the black hole at each iteration. As I mentioned, I added that to the total counter, and later I divided it by the iteration number to find the average mass of the black hole. Here is a representation of that trial. As you can see, that blue arrow represents the perpendicular component of force, the pink one represents the parallel, and the orange represents the net force. In this simulation, we see in the bottom left-hand corner a graph of the net force versus time. As you can see, at that peak, that's right where the yellow ball is on the left-hand side, closest to the black hole of that green orbit. That makes sense because when it's closest to the black hole, the net forces are the highest. Using this data, I determined that the mass of the black hole is 1.678 times 10 to the 34th kilograms. Now some theory into the second part of the lab, don't crash. The perpendicular force on or by a mass is determined in part by its velocity. In this formula, the magnitude of that perpendicular change in momentum equals the mass of that object times its velocity squared divided by the distance. Now, by changing the initial velocity of the ship, we can prevent it from being sucked in by the gravity of the planet or of the black hole. And this initial velocity is found with some guess and check. We can also get the ship to orbit the planet or the black hole with that proper initial velocity. Now, into my code, I used the mass found in part 1, the time, which was also a little bit guess and check. That comes in later. You'll see how I found that. Then I, again, guess and check for the ship speed. Using the information in line 47, I was able to get a rough estimation and then go based on there. Next, I essentially do the same math 4 times to find the force of gravity on these different systems. First, I have the black hole on the planet, then the ship on the planet, then the black hole on the ship, and then the planet on the ship. It's important to note that these are attractive forces, meaning they are negated. So then I go and find the F net on the planet by adding those two forces, then the F net on the ship, again adding those two forces. I then use the velocity and position update formulas to find the change in velocity and position through each step of the ship and planet. Here's a video of that simulation. I'm not going to show the whole thing, but you can see the pink line, the ship, gets pretty close to the black hole and does not hit the orbiting planet. Here's an image of the finished simulation where the planet has made its full orbit, and as you can see, even though those lines intersect, they cross at different times, so they don't actually hit each other. In the upper left-hand corner, you can see the ship speed, which guess and check, and you can see I did not crash. So what does this all mean? Since F net and dp dt are numerically identical, Their parallel and perpendicular components are also numerically identical. However, the rate of change of momentum can be directly calculated via observations in this lab. Fnet needs mass to be directly calculated, and since that's what we're trying to figure out, you can't actually calculate Fnet directly in this lab. Now, what if we wanted the ship to orbit the black hole and not hit anything? So to do that, we'd have to have the same speed as the planet, which orbits the black hole. And in order to accomplish this, I used the same speed, but moved the initial position. So this has been my lab 3, Hope you learned something, and have a good day.